Example 1 on lesson 85, we got a system of equations. Notice that it is a non-linear system of equations. So 2x minus y equals 3 makes the line, but x squared plus y squared equals 9. Once you start squaring things or multiplying letters together, you're going to get curvy lines. And that one specifically, you don't have to know this to be able to do the problem. But x squared plus y squared equals 9 makes a circle. And 2x minus y equals 3 makes a line. So you can see that a line can intersect a circle twice. It could intersect the circle one time, or might not even intersect at all. So there's a possibility of 2 answers, 1 answer, or no answers for a problem like this. Okay, usually at this point in time, they're going to give you the ones that give you the most answers. So just keep that in mind that you're going to get, your empty set doesn't happen in these problems. You're going to get answers. They're going to intersect somewhere. All right. Now, back when we learned elimination and substitution, I taught you substitution first, and then later I taught you elimination, and eventually everybody falls into the I like elimination better camp. Most everybody. I can't remember the last student I can think of that actually by this point in their math career says I like substitution better than elimination. Most people like elimination better. The reason I do substitution first because I like elimination better also, as most people do. But the reason I do substitution first is that way you get a lot of practice with substitution before you get elimination, before you fall into that I like elimination, I'm never using substitution again, get away from me substitution. Substitution has to be used on this one. Elimination won't work. All right? In order for elimination to work, the types of variables have to be exactly the same. X, X, Y, Y, but X squared is not the same as X and Y squared is not the same as Y, so elimination will not work on this problem. We have to use substitution. And going back to our principles of substitution, the one thing I'm looking for if I'm going to do substitution is a coefficient of 1 or negative 1. Solving for that would be easier. And for me, if I got a negative 1 coefficient, I'm going to move that term over here, I'm going to move that over there. So I'm going to get 2x staying where it's at, 3 becomes negative, y becomes positive. I could have also moved the 2x over and changed all the signs in the equation. I just think it's easier to move the negative term. So make y positive, move everything else over there, and all of a sudden you get this nice expression representing y. So if we go up to the top equation, the way substitution works is once we know what y equals, we got to go back to the other equation and substitute. So x is staying x, so x squared is staying x squared. We're changing y into 2x minus 3, and that's supposed to be squared equals 9. All right. Same rules as always with substitution. If I replace a single object y with multiple objects 2x minus 3, parentheses have to go around my substitution. Whatever is happening to y is happening to the parentheses. So y is being squared, the entire contents of the parentheses are being squared there. Okay. Binomial squared happens a lot in these problems. So we're going to use our little shortcut for squaring a binomial. Underline, box that up in red, see where it comes from. So x squared staying x squared. When I square this binomial, I'm going to get plus 4x squared minus 12x plus 9 equals 9. And I'm going to very shortly stop explaining this whole squaring the binomial thing because we've done it 150 times. But just one more time, just for old time's sake, square the first object, square the last object. Both squares are positive. And you double the product. Negative 6x doubled is negative 12x. That's how you square a binomial. That's how we always square a binomial forever. All right? By substituting y out, replacing with an x expression, notice the only letter left in this problem is x. That makes it a workable equation. Since it's quadratic, I want everything equal to 0, so I'm going to move the 9 over here. That gets me 5x squared minus 12x is equal to 0. Now, here's another trap that some of us fall into. We have a quadratic equation. We've got the quadratic formula, right? We have completing the square also, which some of you are still doing, which is fine if you want to do it that way. The quadratic formula is more efficient, all right? But we fall into the trap of every time we see a quadratic equation, we throw it into the quadratic formula without thinking first, all right? This quadratic equation, 5x squared minus 12x, has no constant, all right? If it has no constant, that means it has a common factor of x. Very easily factored. And if you factor out that x, we're left with a factored form equal to 0, which means either x equals 0 or 5x minus 12 equals 0. X equals 0 is already done. 5x equals 12, so x equals 12 fifths. All right? Now, when you do these problems with the nonlinear systems, this happens quite often where you get multiple answers. All right? This says x, this says x, that says x, that says x. Make sure your variables are not being abandoned in your work. Make sure they're sticking all the way through there. X equals 0, x equals 12 fifths. We're looking for ordered pairs. And we know we're supposed to get an ordered pair for a type of problem like this. And sometimes we see two answers, and all of a sudden, hey, there's two answers. I'm supposed to have two answers. There's my ordered pair. All right. X equals 0, x equals 12 fifths. We only have the x answer for both of our points of intersection. Because again, the original picture I gave you was a circle with a line through it, right? 1 point of intersection, 2 points of intersection, 1, 2. To get the y value for each of these, I got to go back here and replace this x with 0 and 12 fifths. So y is equal to 2 times 0 minus 3. That's negative 3. X equals 0, y equals negative 3. Y equals 2 times 12 fifths minus 3. And that's going to be 24 fifths, right? 2 times 12 minus 15 fifths, common denominator, that makes 9 fifths. Zero, negative 3, and 12 fifths, 9 fifths are the two solutions to the problem.